In the last class, we looked at flow, one-dimensional flow with heat addition, where the scenario was something like this. We had a duct of a constant cross-sectional area, and fluid enters the duct at state 1 and exits at state 2 with a certain amount of heat being added. In terms heat, this is heat in units of kilojoule per kilogram, that is what is being added. And starting from state 1, we sketched the possible downstream states. So, the state here is given as for example P1, T1 and U1 is known. So, consequently the stagnation pressure and the stagnation temperature is also known. So, we need to determine what the exit state is, knowing all the other quantities. And we had drawn the states on a TS diagram, which looked like this. So, this is a TS diagram, and we said that starting from state 1, all possible downstream states lie along Rayleigh line, which we denoted like this. So, if state 1 happens to be a subsonic state and we add a certain amount of heat, then state 2 say can be somewhere here, right. State 2 can go up to here for a certain value of heat. Now, if you increase the amount of heat that we are adding, then state 2 can go all the way up to there. And if I keep increasing the amount of heat, the state 2 would move further and further down this line until we hit the location which is the sonic state, where the Mach number corresponds to m equal to 1. So, this is for this is how the downstream states are when we add heat to a subsonic flow, right. This is what we showed the other day. So, depending upon the amount of heat I add, starting from state 1, my state 2 can be here, here, anywhere along this line until the sonic state. So, I can in fact, if I add enough amount of heat, I can accelerate the flow from a subsonic Mach number m1 all the way to a sonic Mach number m is equal to 1 with an appropriate amount of heat. The question of what happens if I add more than this amount of heat is something that we will answer further down. After we discuss a few other things, we will talk about this issue. What happens if I add more heat than what is permitted here? Okay. And if you remember in the subsonic branch, so this is the subsonic branch of the curve, and in the subsonic branch of the curve, if you remember, the shape of the curves is such that the pressure actually P2 is less than P1, pressure decreases with addition of heat and density also decreases with addition of heat. Now, if state 1 happens to be a supersonic state, then we start from here, this is state 1, and once again depending upon the amount of heat that I add, my downstream state can lie anywhere along this until I reach the m equal to 1 point. So, if I add heat, then I travel along this curve in this direction, and if you also remember that in the case of a supersonic flow, this is P equal to P1 and this will be P equal to P2. The Rayleigh line is steeper than the isobar, so the pressure increases when I add heat to a supersonic flow, and the density also increases when I add heat to a supersonic flow. So, this is the supersonic branch of the curve. Okay. And you should also keep in mind that this curve is drawn for a fixed value of mass flow rate and cross sectional area. In other words, this curve is one along which this quantity g, which is m dot over A, is a constant. So, if I have a different value of g, then the curve will be different, same shape, same inferences, but it will be different. Okay. So, these are the important information that we can get from the TS diagram. Okay. And we started doing the same thing on a PV diagram, and this was what we had done in the earlier class. The Rayleigh line remains the same. If you remember, we wrote down the equation for the Rayleigh line as P1 minus P2 divided by V1 minus V2 is equal to minus G square. So, this is a straight line with a negative slope on the PV diagram, and if you remember, the Rayleigh line itself was, so if this is, let us say this is my state 1, then the Rayleigh line has a negative slope which means that the downstream state cannot lie in the second quadrant. So, this is not allowed, or this quadrant. The third quadrant is also not allowed. So, the downstream state 2 can lie in this quadrant or in this quadrant, and if it lies in this quadrant, then if you remember, we said that the downstream state can lie anywhere along this line. For example, it can be here, let us say this is 2, or it can also look like this, where the downstream state is something like this, because we have to make sure that the entropy increases. S2 minus S1 should be greater than 0. So, we need to think about that. We will discuss that as we go along. Notice that this is the pressure axis, this is specific volume. Notice that in this case, as I go from 1 to 2, the pressure increases, specific volume decreases, which means density increases. So, that means this is the supersonic portion of the Rayleigh line. So, this is the Rayleigh line on TS diagram, this is the Rayleigh line in a PV diagram, this is the supersonic portion of the Rayleigh line. This means that M1 in this case, if the state lies here, then M1 is greater than 1, and as we know, M2 is less than M1, the Mach number decreases in this case, right. Pressure increases, density increases, Mach number decreases, right. So, this then is the subsonic portion of the Rayleigh line, and the Mach number increases as we travel along this line. So, for different amounts of heat, the downstream state would lie at different parts of this, at different points along this curve. Okay. That is the information that we are going to bring in next. With this information, or with whatever we have here, we do not know where state 2 is going to be. Okay. In order to know that, we need to bring in the H line also into this diagram. Okay. So, this is where we had stopped in the previous class. Now, we are going to look at the H curve, and if you remember, the energy equation for this case looks like this: H1 plus U1 square over 2 plus Q is equal to H2 plus U2 square over 2. And one important note about this quantity Q is, remember, the enthalpy has units of kilojoule per kilogram. Okay. So, this has units of kilojoule per, usually kilojoule per kilogram or joule per kilogram. This quantity also has the same units. This is actually Q dot divided by M dot, okay, where Q dot is kilojoule per second rate at which we are adding heat, and M dot is the mass flow rate, which is kg per second. So, that this comes out to be in units of kilojoule per kilogram. Remember, this is a flow situation. So, everything has to be a rate quantity. So, that is why this is kilojoule per second, this is kilogram per second. Okay. That is what this Q is. It is important to keep that in mind. Okay. So, this is our energy equation, and if I do the same thing that we did earlier, for example, if I write this as gamma R over gamma minus 1 times T1 plus U1 square over 2 plus Q equal to gamma R over gamma minus 1 times T2 plus U2 square over 2. And from continuity equation, we know that rho 1 U1 is equal to rho 2 U2 is equal to G. So, I can substitute for U from here. If I do that, then I get the following. This equation becomes gamma R over gamma minus 1 times T1 plus G square times V1 square over 2 plus Q equal to gamma R over gamma minus 1 times T2 plus G square V2 square over 2. And if I go through the same algebraic manipulation that I did earlier with Q being equal to 0, if I do the same algebraic manipulation, I can show that this equation can be written finally in the same, almost in the same form as earlier. P2 over P1 is equal to V2 over V1 minus gamma plus 1 over gamma minus 1 minus 2Q over RT1 divided by 1 minus gamma plus 1 over gamma minus 1 times V2 over V1. Notice that if I set Q equal to 0, I recover the equation that I heard earlier with in the context of normal shock waves. So, normal shock wave, of course, Q is equal to 0. Now, Q is not 0. So, the shape of the curve does not change. All we are doing is adding one constant quantity to this, right. So, we are going to get the same type of curves, but curves which are shifted by a certain value depending upon the value of Q. Okay. So, let us go ahead and show this on a. So, this is the equation for the H curve in the case of heat addition, correct. So, we are going to let us draw the H curve on a PV diagram. I am sorry. So, once again states here are not allowed, we know that much. So, let us hatch these regions. So, this is the PV coordinate space. So, the H curve which passes through 1 corresponding to Q equal to 0 will look like this. So, this is the H curve corresponding to Q equal to 0, right, that we had earlier. So, any value non-zero value of Q will give me a new curve which looks like this. So, if Q is non-zero, then positive and non-zero, then the curve gets shifted by an amount like this. So, the new curve would look like this. So, this is Q greater than 0. So, if I add more heat, then the Q line will move up even more, like that. But note that any state in this quadrant is not allowed. Okay. The downstream state can lie on this H curve, but in this or this coordinate, not in this coordinate. I am sorry, not in this quadrant. Okay. So, this is what the H curve looks like for the case with Q not being equal to 0. Notice that we are talking only about heat addition here, that is the most important application. So, we are focusing our attention on that. So, this is state 1. State 2 will lie not on the same curve, but in one of these curves. So, if this is the amount of heat that I am adding, state 2 can lie maybe somewhere here, here or here, or it has to lie here, here or here. In the case of the normal shock solution, if you recall, state 2 also will be on the same H curve because Q was 0. So, both state 1 and state 2 will lie on the same H curve in the case of the normal shock solution, but here state 2 will lie on a different H curve. Okay. Now, we were talking about the entropy for the states in this quadrant. We wanted to ensure that entropy increases. Now, if you again recall from our earlier lecture, the H curves are steeper than the isentropes, right. So, H curves are steeper than the isentrope. So, the isentrope passing through state point 1 will look like this, which means that any downstream state, for example, normal shock solution, if any downstream state lies on the same H curve, then the entropy for that state will be less than this. So, this is S equal to S1, right. So, if the downstream state lies on the same H curve, then the entropy will actually reduce, which was why we said that the downstream states for that case cannot lie in this quadrant. But notice that in the case of with the heat addition, the downstream states will have entropy greater than S1. So, any of these states will have entropy greater than S2, greater than S1, and so states in this quadrant are also allowed when we have heat addition or heat removal. Okay. If there is no heat addition or heat removal, then the downstream states cannot lie here because S2 will become less than S1. With heat addition, you can see that this isentrope comes like this, so all these states will have higher entropy than state 1. Okay. So, what we are going to do now is combine the H curve with the Rayleigh line diagram, so that the point of intersection of these two will tell me where the downstream state is. That is what we are going to do next. So let us see how we go about doing that. So here we have indicated the Rayleigh line. So let me draw a Rayleigh line here in this part. Right, so that is a Rayleigh line. And let me draw one more Rayleigh line which looks like this. Okay, so this and this are both Rayleigh lines. So if this is the amount of heat that I add, then my state, downstream state, let me remove this S equal to constant line because it's a little bit confusing. So if this is my Rayleigh line, then if this H curve corresponds to the heat that I am adding, then my downstream state is going to be right there. Right? This is the, remember, this is the supersonic branch. So starting from state 1, which is over here, I travel along the Rayleigh line, I reach state 2. Okay? One very important thing that you should keep in mind is, let us say this corresponds to say 50 kilojoule per kilogram. Okay? Same duct, if I add 40 kilojoule per kilogram, then state 2 would lie probably somewhere here corresponding to a different H line, right? That H line might look like this, right? So the state will lie here. So what this means is that starting from state 1, all the subsequent states will lie along this Rayleigh line until we hit state 2, right. That is a very important distinction between this and the normal shock solution, okay, that we must pass through all the subsequent states. If you remember, we discussed this earlier. So starting from state 1, I add a little bit of heat, I get to a new state, then I add a little bit of heat, I get to a new state. So that means I am traveling along the Rayleigh line and cutting across many of the H lines until I reach the exit where the total corresponds to this. Okay? So that means I must pass through all the intermediate states from 1 before I can reach 2. I cannot jump from 1 to 2. This is not a wave solution, this is a continuous solution. That is a very important distinction because that brings in certain limitations on the amount of heat that we can add, okay, which we will discuss afterwards. Now similarly on the subsonic side, for example, I can show a H curve like this, like that, and my downstream state will then lie here. So starting from 1, I go up to 2, so you can see that I am traveling along this Rayleigh line to go from 1 to 2, where this is the amount of, this is the H line which corresponds to the amount of heat that I have added. Okay? Is that clear? Now, if you remember what we said about the Rayleigh line on the TS diagram, you will remember that starting from 1, if I add an amount of heat which I call as Q star, then the state at the exit of the duct can become the sonic state, that is M becomes equal to 1. And if you remember, we determined that this was M equal to 1 because we had the equation for the Rayleigh curve, right? We had dt ds for the Rayleigh curve, and we said that as M goes to 1, on the subsonic side dt ds goes to minus infinity. So which tells me that this is a state where M is indeed equal to 1 and the slope is becoming minus infinity. We did the same thing for the supersonic branch also. Now here I need to see where the sonic state is going to lie when I draw these types of lines. Right? Where will the sonic state be? So if you take any one of these branches, let us start with the subsonic branch because we have been looking at that. So as I travel along this subsonic branch, the Mach number, remember M1 is less than 1 and M2 is greater than M1. So M1 keeps increasing. As I add more and more heat, M2 becomes higher and higher. If I add a little bit more heat, then I will go further down here. So at some point, right, I can see easily that there is a H curve for which the Rayleigh line is tangential. As I keep going further and further down, as I add more and more heat, there is going to be one H curve which is such that the Rayleigh line is tangential to that point, at that point. Okay. Similarly, on the top side, if you look at this, there is going to be one H curve where I become tangential. So if I extend this line, there is going to be one H curve where the Rayleigh line becomes tangential to the H curve. Intuitively, you realize that that is the point where we reach the sonic state, we attain the sonic state, but we need to prove that. In the previous case, we clearly showed mathematically that as m approaches 1, dt ds approaches minus or plus infinity. So here we need to prove that at this point of tangency, both here and here, that the Mach number is equal to 1. Okay? So that is what we are going to do next. So in order to do that, we start by rewriting the H equation in a very generic form. Okay, so I am going to take this equation and write this like this. So gamma r over gamma minus 1. So what I am going to do is I am going to take this RT1 and write the RT1 as P1 V1. Right. So RT PV equal to RT. So I can take the RT1 and write it as P1 V1, and the second term becomes G square times V1 square over 2 plus Q is equal to gamma over gamma minus 1. I am going to write this as PV, so that the downstream state can lie, as we move along that line, the downstream state can be any value of P comma V plus G square times V square over 2. So if I differentiate this with respect to V, to get the following, we can do this very easily. It is very easy to show. We can rearrange this like this, dp dv, and let me explicitly say that this is dp dv for the H curve, right. This is a slope for the H curve. So dp dv is equal to minus gamma minus 1 over gamma times G square minus P over V. So this is the slope of the H curve at any point. Now at the point of tangency, right, so if you look at the point of tangency, which is this one here, let me show that with a circle. So the point of tangency, both this one and this one, the slope of the H curve is equal to the slope of the Rayleigh line. And what is the slope of the Rayleigh line? Minus G square, right. So we equate this to the slope of the Rayleigh line. So at the point of tangency, the slope of the H curve is equal to the slope of the Rayleigh line. And the slope of the Rayleigh line itself is minus G square. So we equate this to minus G square. So, minus gamma minus 1 over gamma times g square minus p over v is equal to minus g square at the point of tangency. So, simplify this and we get this to be p over v is equal to g square over gamma Now, if you use the fact that g is equal to rho times u and v is the reciprocal of the density, I can easily show this thing to be u is equal to square root of gamma times p over rho. And what is this equal to? Speed of sound. So, at the point of tangency, the speed is equal to speed of sound, which proves that at the point of tangency m is indeed equal to 1, right. So, at the point of tangency or sonic state, the Rayleigh line becomes tangential to the H curve. Now, once again we asked this question earlier, what happens if I add an amount of heat which is more than what is required to reach the sonic state, right. The amount of heat that we add to reach the sonic state, if you denote that as Q star, what happens if I add an amount of heat more than Q star, right. So, in that case we can see that the H curve, so if this is the H curve corresponding to Q equal to Q star, if I add heat more than Q star, then I have my downstream state would have to be on this H curve. But how do I get on that H curve, because this has already become tangential, right. How do I get onto that H curve? Or similarly here the H curve is over here, so how do I get onto that H curve if this has already become tangential? So, some changes have to take place, right. So, that is what we are going to discuss next. So, we answer this question like this. So, if m reaches the sonic state at the outlet of the duct, that means the flow is said to be choked, right, and m2 becomes equal to 1, then the flow is said to be choked. Now, choking can be due to a variety of reasons, okay. In this case choking is due to heat addition, that is why this type of choking is called thermal choking, right. So, here choking is due to hence this is called thermal choking. Anytime the flow reaches m equal to 1 at some point in the flow field, we say that the flow is choked, okay. And if you recall m equal to 1, we discussed that in the case of in the first chapter we said that m equal to 1 is a very important state because separates regions of flow over which we have control and regions over which we do not have full control. Okay, so choking is a very important aspect of the flow field, and when m just reaches 1, then the flow is said to be choked. And notice that m will for m to reach this, the amount of heat that we add, we will denote that as q star. So if you add an amount of heat q star for a given value of m dot and a, the exit state becomes sonic. What if I add more heat than q star? That is the question that we wish to answer. So what if the q that we add is greater than q star for the given inlet Mach number? So every inlet Mach number will have a corresponding q star, right. So if the inlet Mach number is 0.3, q star will have some value. If it is 0.4, q star will be less. If it is 0.5, q star will be even less. So every inlet Mach number has a q star. So the question is, what if I happen to add heat which is greater than q star? That is what we are going to discuss. Now we will classify or differentiate our answer into two cases, one for the subsonic inlet Mach number and one for the supersonic inlet Mach number. So let us first look at the case when the inlet Mach number is less than 1, subsonic case, q is greater than q star. Where will the downstream state be? That is a question that we wish to answer. Let us start with the PV diagram and see if we can answer this question somewhat easily there. So let us see. So this is our PV diagram, and let me say that this is my state 1. These states are not allowed. So let us say this is my Rayleigh line. So this is q equal to, but I am trying to add an amount of heat which is more than q star. So that means the H curve that I want is this. So I want the downstreams, I am trying to add this much heat to the flow, okay, whereas the q equal to q star H curve looks like this, so that there is a point of tangency here, and this is the sonic state, right. So this is the sonic state where m is equal to 1, and this is the subsonic branch that we are looking at. So how do we, you can realize that if I keep going this along this line, I cannot really go past this point, because if I physically try to go past this point, that means that now I am intersecting H curves for which the value of heat is less. So I am not removing heat. In order for me to attain this curve, there is one way I can do this, and that is to change the slope of my Rayleigh line. What if I operate on a Rayleigh line which has a lesser slope than this Rayleigh line? Let us say that we show it like this, right. So let us say that we operate on a Rayleigh line which looks like this. So let us say that we operate on a Rayleigh line which looks like this, and you can see that this Rayleigh line, I can operate on this Rayleigh line up to this state point, right, and I can still add this much amount of heat, but now the amount of heat that I am adding will correspond to q star, so that it becomes tangential to this H curve. So that is the only way I can get on to a higher value of heat. So slope of the Rayleigh line, if you remember, is equal to minus g square, and g itself is defined as minus m dot divided by duct area square. So, how do I operate on a Rayleigh line with a lesser value of slope? Either increase the area or decrease the mass flow rate, right. So, either I increase the area of the combustor or I decrease the mass flow rate. Notice that in this diagram I have shown the static state 1 to be at the same location, but when you start to operate on a new Rayleigh line, state 1 may not be the same state 1 as what we had earlier, right. So, we had a duct, we started with a certain inlet state, we are adding a value of heat which is more than Q star for that state. So, now when I change the cross sectional area or the mass flow rate, that state 1 will no longer be the same state 1 as before. Now, the state 1 becomes different, right. So, the static conditions, so this means that the static conditions at the entrance to the duct change. So, they will be different from before. Notice that stagnation conditions cannot be different, right. Why cannot stagnation conditions at entry to the duct be different? Why do they have to remain the same? Because stagnation conditions, if you remember, can be changed only by addition of heat or work. So, if I want stagnation condition at the entrance of the duct to change, that means I must add heat or work before the entrance of the duct. So, stagnation conditions cannot change, only static conditions will change. Stagnation conditions at the entrance will not change. Yeah.
Stagnation pressure will also not change.
No, the stagnation pressure at the entry to the duct cannot change, or the stagnation temperature, because those can be changed only by addition of heat or work. So, if you remember, if this is my duct and this is the entrance, right. So, the flow comes like this, flow goes out like this is my state 2. So, if I want to change the stagnation condition here, right, what should I do? I should add heat or work before this place. This cannot do that, right. I am adding heat here, so I cannot change the stagnation conditions here. Stagnation conditions will remain the same, static conditions will be different. Okay. So, that is what happens. So, we go on to a different Rayleigh line on the PV diagram. The same thing if I want to illustrate on a TS diagram, it looks like this. And this was the TS diagram that we had. Right. So, we started with the subsonic state, and this is the sonic state corresponding to m equal to 1 with the addition of heat. So, if corresponding to this value of m1, the heat to be added is more than Q star, then we can no longer operate along this curve. So, we have to get on to a new Rayleigh line on the TS diagram. The new Rayleigh line would look something like this. And remember, G decreases in this direction as you move outwards. So, the new condition, and remember, this is my T01, this is my P01. So, the new static condition will be such that T01 and P01 remain the same, but the static conditions are different. So, I now get on to a new curve which I call as 1 prime. So, my new operating point is along this line, right. So, I operate along this line, and the heat that I am adding is such that it is equal to Q star corresponding to the new static state. Okay. If you remember, this is what we did here also. So, I got on to a new Rayleigh line, and the Q was such that it was equal to Q star corresponding to that H curve. And similarly here also, the new Q is Q star corresponding to this Rayleigh line. It need not actually be equal to Q star, it can be slightly different than Q star depending upon the downstream condition, but for simplicity's sake we will simply assume that to be Q star corresponding to the new operating condition. Okay. So, this is what is illustrated in the next figure. Let us take a look at this figure. So, this is what is illustrated in this figure. So, you can see that we initially started at state 1 and this was the Rayleigh line that we were operating along, and the Q that had to be added was more than Q star corresponding to this Rayleigh line, which means that the T01 and P01 remaining the same, we go from state 1 to a state 1 prime, which lies on a different Rayleigh line, which is shown as a thick line here. So, the amount of heat that we are adding now is equal to Q star corresponding to this entry condition. Okay. For entry condition 1, the amount of heat Q would be more than Q star corresponding to M1, but now the Q is the Q star corresponding to M1 prime. Okay. So, that is what happens if we have a subsonic state and we try to add an amount of heat which is more than Q star. Now, this kind of adjustment of the inlet condition, so this is the duct, so if you add more heat, the inlet condition, static conditions adjust itself so that either there is a reduced mass flow rate normally if you keep the area the same, or we can do other things, right. Changing area is much more difficult practically. Okay. So, if you add too much heat, then the inlet conditions change for a new mass flow rate. This is possible only because M1 is a subsonic Mach number. So, any changes that you try to do here, if the heat is too much, then the flow can sense it and adjust itself so that it accommodates the new heat release with a reduced mass flow rate. This is possible in a subsonic flow when M1 is less than 1. This is not possible in a supersonic flow, right. Supersonic flow is traveling at high speed with speed greater than the speed of sound. So, such an adjustment will not be possible in the case of supersonic flow. So, something else has to take place in a supersonic flow. That is what we are going to discuss next. So, the next case that we are going to look at is when the inlet Mach number is greater than 1 and the Q that we are adding is greater than Q star corresponding to this inlet Mach number. So, once again we are looking at this type of a situation. Now, M1 is greater than 1, this is state 1, exit is state 2, M1 is greater than 1 and the heat that we are adding is greater than Q star corresponding to M1. So, depending upon how much greater, in this case as I said earlier, we cannot, there is no option of going back and changing the inlet conditions, right. The information cannot propagate upstream. Right. So, depending upon how much Q is greater than Q star, right, we try to add too much heat and the remember the pressure, it keeps increasing. In a supersonic flow with the addition of heat, the pressure keeps increasing. So, depending upon how much Q is greater than Q star, eventually what will happen is a normal shock is triggered somewhere inside the duct. Okay. So, you have a normal shock at some location in the duct which looks like this. So, the Mach number is greater than 1 before the normal shock and it becomes subsonic afterwards and you continue to add heat. So, the same heat can be accommodated, but with a normal shock here. Of course, with a normal shock you know that there is a further loss of stagnation pressure which is undesirable. So, we have a normal shock here. So, if I show this process on a TS diagram, it will look something like this. So, we are operating at a supersonic, in the supersonic branch of the curve and we are adding heat which is more than the Q star corresponding to state 1. So, which means that we add heat up to a certain point and then we have a normal shock which appears like this, and then we switch to this part of the curve. So, if I denote the state just ahead of the normal shock as state point as x and just downstream of the normal shock as y, then this is state point x, this is state point y, and this would be my state 2. So, we start from the supersonic portion of the Rayleigh line, we go up to x and there is a normal shock, then we operate like this. The location of the normal shock both here or here will depend upon how much Q is more than Q star. If Q is only slightly more than Q star, then this normal shock will be further down. As I keep increasing the Q, this normal shock will keep moving further and further up. Eventually, the normal shock may stand at the entrance to the duct itself. As you keep increasing the pressure or the heat addition, it can even move and stand in front of the duct, so that the flow can become subsonic the entire duct. That is also possible. That is not equivalent to a change in inlet conditions, right. Remember, as you keep increasing the pressure, right, even the normal shock would have to travel upstream as you keep increasing the pressure. And there is an extreme case when it can move out and then stand in front of the duct. Yeah, go ahead.
Exit Mach number is always 1.
Exit Mach number need not always be 1. Exit Mach number will depend upon what components you have further down the device. If this is a combustor and we have something else down the device and there is a pressure that is applied here, if this pressure is fixed, then the exit condition will adjust itself to suit that exit pressure. Okay? If I am prescribing a certain pressure downstream of this, then when the flow comes out, the pressure, static pressure of the flow will most likely match the exit pressure that we are imposing. Okay? It need not always be 1, but for the sake of simplicity we are just assuming it to be 1. It can be anywhere else depending upon the pressure that I am imposing. Okay? Now, the more difficult question is, how do we illustrate this on a PV diagram, right? So, this is my Rayleigh line, this is my state 1. The important difference now is that I stay on the same Rayleigh line, I am not going from one Rayleigh line to next like I did in the subsonic case. So, here we have to be, all the states must lie on the same Rayleigh line. Okay? So, let us say that this is the this is the heat that I am adding, Q greater than Q star. So, there is no way I can reach states on this using this Rayleigh line, it is not possible for me to do that, right. So, because the Rayleigh line becomes tangential at some point here. So, the Rayleigh line becomes tangential to the H curve at some point here. So, this is Q equal to Q star. So, the actual Q that we are adding is more than the Q star. So, I cannot go to those types of states. So, what actually happens is I travel along this up to some value of Q. I travel along the Rayleigh line up to some value of Q. So, this would be my state X. Now, each Rayleigh line intersects a H curve at two locations, okay. Though it is not clear in this picture, let me show you a different picture where that is made very clear. So, each Rayleigh line intersects as you can see from here, each Rayleigh line intersects a H curve at 2 locations, one here and one there. So what happens in this case is the Rayleigh line intersects the H curve at this location, and then we go on to and then we have a normal shock wave. So state y, we are going to jump from here to the other point in this Rayleigh line where this intersects the H curve again. So that is my state y, and then I travel up to this point. Okay. So I jump from this x to another state which is along this Rayleigh line, which will intersect this, and if I extend this will go and intersect this line. So that is my state y, and then I come back to this point. So this is my state 2. Okay. I can jump from x to y because the normal shock solution is a discontinuous solution. So basically what I am doing is I am starting from state 1, going up to some value of q, right, and then I am normal shock is triggered. So I stay on the same Rayleigh line and the same H curve. Notice that y must be on the same H curve, it cannot be on a different H curve because there is no heat addition into the shock wave, right. So I must stay on the same H curve. So I go from this state which I label as state x, and then we go to state y which is on the same H curve and same Rayleigh line which is state y, and then now I begin to move down like this, which means further heat is being added now until I reach a location here where state 2 is located. So this is where we are here. So you can see clearly that 1x here corresponds to this portion of the Rayleigh line. The xy here, normal shock solution, is a discontinuity, so we go from x directly to y without going through this point. That is the difference. I do not have to go through this point in a normal shock wave. I can go directly from a supersonic to a subsonic Mach number without going through the sonic state. That is the advantage of a normal shock. I do not have to go through the sonic state to go from supersonic to subsonic. Whereas in the Rayleigh flow, I have to go through the sonic state. Right? So I can go from here to here and then I go back here. So that is this portion of the curve where I go back from there to here, which means continuous heat addition further. Okay. We will do a worked example in the next class and then move on to the next chapter.